All right, so I just wanted to start off by asking if you have any specific questions related to what we did yesterday. I mean, we weren't doing anything sophisticated really. We're just looking at conversion from hexadecimal to, I believe we ended at stage where we're looking at conversion from hexadecimal to binary. But we also looked at conversion from binary to hexadecimal really. We realized that the best approach for doing the conversion is to group the binary, like when you are converting from either from hexadecimal to binary or binary hexadecimal, is you group your binary digits into groups of 4s, right? So-called nibbles or half a byte really. And we looked at some examples. We mostly used the example associated with, I guess, the status of Lighton's Qt spin, right? So if you remember, the conversion that Lighton was using is this, right? So if I open up my Qt spin, the status of the registers is shown to me. So we were using these things here to do the conversion, right? I did mention that we would continue off our conversation by really looking at some of the examples that we have here, hopefully to reinforce the discussion we started yesterday, and perhaps try and see if people have any specific questions associated to this, right? So we're just going to skim through some examples of conversion from hexadecimal to binary, right? Starting with A to DE, right? Again, for most of these conversions, and in fact, most of the things we're going to cover in ICT 1110, including these other courses we're going to be looking at, things like 2010 next year, for instance, 2021, I'm not sure about 2022. It turns out that everything is just centered around rules and conventions, right? Rules. So in this case, I guess what I'm trying to say is if you want this to work, you just have to make sure that you follow the rules, right? And of course, you don't have to follow the rules that Lighton is laying out as we're interacting together. It's entirely possible that you might find other rules online somewhere out there, perhaps a much easier to work with method, right, for doing these computations. That's fine, as long as you stick to it, right? Just follow the rules. So converting A to DE base 16 into base 2, for instance, we're saying the first thing we need to do is we convert these hexadecimal symbols into their equivalent decimal symbols. Now, this example here is pretty interesting because we have three of the 4 symbols are symbols that are not associated with the 10 decimal symbols that we normally work with. And so what do? We need to identify the corresponding decimal equivalents. So A is 10, 2 of course is still going to be 2, D is 13, E is 14. And then using these decimal numbers, we convert to binary using 4-bit representation. Right? So whatever answers we're getting as we're converting these decimal numbers here, 10, 2, 13, and 14, into binary, we have to use 4-bit representation. If your answer only has 1 digit, 1 binary digit, you prepend it, or you prefix it with 3 zeros so that it's represented using 4-bit representation. And finally, the final stage is just group those nibbles together, right? So 10 is 1010, right? This is obvious. We're just adding 8 plus 2, right? 8 plus 2. 1's place, 2's place, 4's place, 3's so 1's place, 2's place, 4's place, 8's place, right? So 8 plus 2. 1's place, 2's place, 4's place, 8's place. So we're adding 8 plus 2 to get 10. 2 is just 0, 1, right? And then 13 is 1101, 14 is 1110, right? And you can confirm this, you can verify these later on. As you are doing this for the first time, I do encourage you to follow the rules we laid out when you're doing a conversion from decimal to binary, right? Because this is what we're doing in the 3rd step here, yeah? For us to get from 14 to 110, we went through our simple heuristic. What is our simple heuristic? We repeatedly divide 14 by 2 until we converge when the result is going to be 0, right? I know for those of you that have already figured this out, that's fine, but we want to make sure we're on the same page here. So it's in decimal to binary 14, repeatedly divided by 2, where you have the result, quotient, and the remainder, right? 2 into 14 is 7, remainder 0. 2 into 7 is 3, remainder 1. 2 into 3 is 1, remainder 1. 2 into 1 is 0, remainder 1, right? Our answer is 1, 1, 1, 0, right? Because we need to flip these. So we have 1, 1, 1, 0. If we were to look at an example that has resulting bits that are less than 4, like this here, we repeatedly divide 2 by 2, right? This is the quotient, this is the result. 2 into 2 is 1, remainder 0. 2 into 1 is 0, remainder 1. What is the answer? 1, 0. Because the answer is 1, 0, the next step will involve us making sure that all of these answers are represented using 4-bit representation, right? So observe this thing here. Instead of 1, 0, we are saying it's going to be 0, 0, 1, 0, right? And then finally, we know that the answer is going to be derived by combining all of these different neighbors or groups of 4s here into one thing. And then this is the answer here. Now observe something, right? If we did not prefix or prepend this 1, 0 with the 2 zeros, our answer was going to be, it was going to be wrong, right? Observe this. This is an important point, I guess. I don't know if you pay attention to what I'm doing here, but if I copy this, what's going on here, but and paste, okay. And what we're saying, right, is if you don't prefix, this is the answer here, right? And you can confirm this, right? This is the answer, you can confirm this with your calculator. But assuming that we missed out the third step here, where, if we missed out this step here, where we made sure that all the resulting solutions are represented using 4-bit representation, would have ended up with an answer that is similar to this here. Observe. This would have been our answer. No zeros here. This would have been our answer. And guess what? If you convert this, if you use your calculator and convert this to hexadecimal from binary, what you will realize is that the answer you will get is going to be different. It's 2ADE, right? So this is equal to 2ADE. When in actual fact, the answer is supposed to be A2DE, right? This is A2DE, but what we got when we did not prefix with the zeros was 2ADE, right? And we can confirm also with the calculator here, right? So you want to be very careful that you follow the rules, right? And you'd get this wrong if you just omitted this part here. Is this making sense?
Sir, do you mind going
Yes, sir.
over it just one more time?
Yeah, well, so we have another example here, but if you, I don't know which part, I can go, yeah, sure, I don't mind going over it again. It's a pretty
Just this example, that's all. Just this part, that's all.
Yeah, I mean, so what we're saying is the rules are simple, right? First step, when you have a hexadecimal number, like A2DE, even if it was 22 in hexadecimal, the first step is you lay out the hexadecimal symbols one after the other as they appear left to right. The next step is you convert each individual hexadecimal symbol in its equivalent decimal symbol. A is 10, 2 is 2, D is 13, E is 14. And then the third step is you're going to convert these decimal symbols now, because these are hexadecimal, these are decimal symbols. You convert the decimal symbols into their equivalent binary numbers. converting them to binary is easy. You repeatedly divide each one of these decimal symbols by 2. Right? So repeatedly divide by 2 until you converge to a stage where the result is 0. And then you lay out the bits one after the other. So if we repeatedly divide 10 by 2, we get 1, 0, 1, 0. We repeatedly divide 2 by 2, we get 1, 0. We repeatedly divide 13 by 2, we get 1, 1, 0, 1. We repeatedly divide 14 by 2, we get 1, 1, 1, 0. The next step is we want to ensure that the binary results here are all represented using 4-bit representation. You must have 4 bits. If you have any result that does not have 4 bits, as is the case for 1, 0 here, what you must do is you prefix or you prepend it with zeros at the beginning until you have 4 bits representing that number. So instead of, so 1, 0, 1, 0 will be 1, 0, 1, 0. 1, 0 will be 0, 0, 1, 0. 4-bit representation. 1, 1, 0, 1 will be 1, 1, 0, 1. 1, 1, 1, 0 will be 1, 1, 1, 0. The key thing here is you must represent the final result, each of the individual symbols that you've converted using 4-bit representation. Otherwise, you will get the wrong answer. You'll be quite sad, really. I don't know. Does that make sense?
Yes,
Yes,
sir.
sir.
Yeah. I don't know how many people we have in the house, but wow. 15. Such sadness. Anyways, yep.
If you mind, can you go through slide 125? I was failing to understand on the answer which you found.
Slide 125.
Yes.
Go to 125. This slide? What is 125 about? Is it before or after this slide?
Not this one.
This one?
No.
Which one then? This one?
1.5.
125 or 35?
1.5.
Yeah, I was on 125. 125 is this slide here, which is why I'm skimming through the slides to find out which exact. What's the question about?
The question was about the converting a binary to hexadecimal, and then the answer was the 12.
Yeah, is this example then, right?
Yeah.
Okay. Okay, let's do this, right? We're saying for us to convert this to hexadecimal, what are the rules? The rules are simple. We first of all split this into groups of 4s, nibbles, right? Splitting this into groups of 4s, we'll have the first group from right to left. From right to left, group number 1 will be 0, 0, 1, 0. The last group will be just 1. Because we have just 1 for this other group, we shall have 1, 2, 3, 1 as the one group, and then the other group will be 0, 0, 1, 0. What do we do afterwards? We convert these into their equivalent. We're supposed to convert these into the equivalent decimal numbers, right? So what is the decimal equivalent of this? This is simple. This is a 1. This is the 1's place. This is the 2's place. So this is 2. This is simple. This is the 1's place, 2's place, 4's place, 8's place. Now this is the thing, right? When you're dealing binary to hexadecimal, just think about it from placeholders. If you have a decimal number like 1, think about this for a second. If you have a decimal number like 2, 1, 1, 2, how do we know that this is 212? We know that this is the 1's place, this is the 10's place, this is the 200's place. So essentially what we're adding is 200 because it's the 200's place, 200 plus 10 plus 2. So for binary numbers, it's the same. 1 to power 2 to power 0, 2 to power 2 to power 1, 2 to power 2, 2 to power 3. This is a ones place. This is a ones place. This is a twos place. This is a fours place. This is a eights place. This is why I can add mentally here, right? I know that this is a two because this is a ones place, twos place. So this is a two. I know this is a ones place, twos place, fours place, eights place. So this is a one, right? Because we have 1, 2 here, these are decimal. To change them to binary, these symbols, to change them to binary, 1 is still going to be 1. 2 is still going to be 2. So in fact, 10010 in hexadecimal is just 1, 2, base 16 in hexadecimal. Does this make sense? Or it's still confusing?
Yes, sir. Yes, sir. I was just missing a certain concept which you said that you have to divide to separate the nankan in 2 laddiks.
Into nibbles or half a byte, yeah, into groups of 4s, right? This is the thing. This is like if you look at if I was to sum up what we're doing right now, once we get to the end, it's just rules, and there are more rules coming by the way. Once we start looking at binary addition, subtraction, multiplication, division, it's all centered around rules, right? What do you do when you're adding 0 and 0? When you're adding 1 and 1? When you're adding 1 and 0? When you're adding 1, 1, 1? Right? This is when you're addition, right? How do you treat that sort of the result that you get, right? So it's just rules, really. I know, so these rules normally stick once you work on these problems. At least you work on a couple of problems for these things to stick in. If you just read this once and assume that you know things, I'm sorry, but it's going to be a bit difficult for you to do these things. Good stuff. So we're going back to 146 where we were, 146. Oh. So we wanted to do a conversion for this other example, 3E8, right?
Oh, Dr. Lighton.
Yes, sir.
Just on the part where we are converting A to DE, base 16 to base 2. And I also found a method, since you said that you should also check for other methods. I also found another method whereby since we are grouping them base 16 values, each X digit, we group them in groups of nibbles or groups of 4. It's also coming in handy where we can just write the powers of 2 up to 4, meaning from 2 to the power of 0 up to 2 to the power of 3, and then any hexadecimal number that we want to convert, we just convert it to its equivalent decimal symbol, and then just replace the ones and zeros of which those ones and zeros makes up the value we have converted to. It's also coming in hand, but if it's okay, I can also show you here. Just a simple one. I was also converting the same one you just converted. Maybe we can also find it useful.
Yeah, I mean, I can pause. I can share my screen. You can share your screen. I mean, I would like to see this, but it sounds to me like the process you're explaining is pretty much similar to what we're doing, where you convert to decimal first. But so I'll stop sharing my screen, and then you can share your screen, and then show us your method. We want to learn something new here.
Are you able to see my screen?
Yes, we can.
Oh, yes. This is the part I was talking about. So I got this question you gave us, converting A to DE to base 2. And then I write the powers coming from, since we're grouping them in groups of 4, meaning we just need 4 nibbles. So you write 2 to the power of 0 over here. You start 2 to the power of 0 up to 2 to the power of 3. And then since we're converting A to DE, I write A over here, and then I convert A to its equivalent decimal, which is base 10. And then on the groups of 4, on these groups of 4, if we evaluate the powers, we have 2 to the power of 3, which is 8, 2 to the power of 2, which is 4, 2 to the power of 1, which is 2 to the power of 0, which is 1. And then in order for us to get 10, meaning we're adding 8 plus 2, so I'll just put a 1 under 8 and a 1 under 2, and the rest I'll just put zeros. And I do the same things for the rest of the values. And then at the end, I just group them together and get the value, which is 101, 0, 0, 0, and 0,
yeah.
and that.
But it's the same thing we are doing. So that the only difference is you are visually don't stop sharing that. You are visually you're showing things. Your visual representation is different from mine, right? what you're doing is the same thing. You are first of all you are converting your base 16 into base 10, and then you are converting the base 10 into base 2, right? So the column where you have A is equal to 10, 2 is equal to nothing, D is equal to 13, E is equal to 14. What you're doing there is you're converting the hexadecimal symbols into decimal. It's the same process we've been doing. And then the part where you have the powers of 1 being represented by 8 is 1, 2 is 1. That's like the 1's place, 2's place, 4's place, and 8's place. You're doing that because you want to get 10, right? You're converting 10 into binary, essentially. This is great, but the point I'm trying to put across here is that it's actually the same thing, right? Process is the same, where you have a hexadecimal number, you convert that number, each of the individual symbols into base 10, which you have in this column C here. A is equal to 10, 2 is equal to nothing, D is equal to 13, E is equal to 14. And then you're converting now the decimal numbers you've derived, 10, 13, and 14, into the equivalent binary numbers, right? So 10 is equal to 1010. But what you're doing, right? What you're doing to get 10 is what I was mentioning, is it yesterday when I was saying you can form a mental picture. For you to get 10, you know that you're adding 8 and 2. How do you get 8 and 2? You know that it's 2 to the power 3 and 2 to the power 1, right? So that's great. I mean, it's a nice way of, this will certainly be much faster than repeatedly dividing 10 by 2, because the only other way you can come up with 1010 is by you repeatedly dividing 10 by 2, the method that we went through. Yeah. But what you're doing here is you're saying, I don't want to repeatedly divide 10 by 2. Instead, I'll use this method where you're just using the powers of 2 to identify. It's like forming a mental picture to try and figure out exactly how you're going to get that answer. It's like in decimal, right? If you can unshare your screen. Well, this is great. Thanks for sharing this. I hope people will be able to look at this method and then try and see if maybe you can utilize this instead, right? It's like when they taught you how to divide in, thanks again, when they taught you how to divide, right? When you're dividing numbers, do you remember you used to draw that funny thing in grade 1 or something? You're dividing a number, let's say you're dividing 21 by 2, no, 22 by 2 or something. You'd do this, right? You'd say, you write, we used to do this, I don't know if they still do this. They taught us how to draw this funny thing here. Why? I don't know, right? So you do this, right? It doesn't necessarily mean that for you to divide, you have to do this, right? You can use a completely different method, but the idea is the same, right? You divide, you get the answer, you multiply the answer, and then you subtract. Do you understand this?
Yes, sir.
Yeah. It's like, it's just a visual representation. So what you're doing is you're saying, instead of visually representing the, which is great, by the way, instead of visually representing things like this, like the way Lighton is doing. And in fact, what Lighton does, right? What Lighton is doing now is, I'm skipping certain steps here. If you notice, hexadecimal to binary, I'm skipping certain steps because I'm assuming that you know how to convert from decimal to binary. Observe in this example that we're trying to go through here, where I was saying for us to convert 3E8, I'm saying the first thing we have to do is to convert each of these symbols into the equivalent decimal symbols. 3 is 3, is 14, 8 is 8, right? In the next step, I'm saying we convert 3 into base 2. Now, I am not going to repeatedly divide 3 by 2 here, because we've gone through this already. I know that you know how to arrive at 1, 1, arrive at 1, 1, 1, 0, arrive at 1, 0, 0, 0. Either you repeatedly divide or you do what Patrick was showcasing. You understand? So don't be deceived by this. I'm just doing this because we've already covered the conversion from this part here. We covered this already. What we're doing here is we're converting base 10 to base 2, right? Anyways, so on with this example here, 3E8, we're saying 3 is 3, E is 14, 8 is 8. Then we convert the decimal symbols, 3, 14, and 8 into the equivalent hexadecimal symbols. And then the key step, make sure that the answers are represented using 4-bit representation. If you have a result that has less than 4 bits, prepend or prefix them with zeros until you have 4, right? So as is the case with 1, 1. Instead of 1, 1, we have 0, 0, 1, 1. Now this is the interesting thing here about this answer is that if you have a situation like this where the last symbol that you're converting has less than 4 digits, it doesn't affect the answer per se. You can remove the 2 zeros, the leading zeros, right? Because it's these are the most significant bits. Why? When you're multiplying these, you still get the same answer. I don't know if I'm making sense, but there's no harm in you saying your answer is going to be 00111110100, right? It doesn't matter, although it's more elegant if you represent it like this, right? You just do away with the zeros. Is this fine?
Sir.
Oh, yes, sir.
What is 11 divided by 3?
I'm sorry?
What's 11 divided by 3?
11 divided by 3?
Yes, because 11 divided by 3, isn't it 3 times remainder 2?
Well, I don't know. I mean, I can divide here. 11 divided by 3 is 3.
Remainder 2, right?
Yeah, but why are you talking about, why are you dividing 11 by 3?
Because the answer you've given there is 0011 for 3 divided by.
Yeah, but we're not dividing. What we're doing here is we're dividing this decimal symbol by 2, right? So what we're saying is that once we are dividing the 3 by 2, not 11. There's no 11 here, by the way. This is 1 1. This is not 11.
Right.
This is 2. So we're saying 2 into 3 is 1. What's the remainder? The remainder is 1. 2 into 1 is 0. What's the remainder? 1. Right? And then the answer is 1 1, not 11. 1 1, right?
Oh, right.
Okay, good stuff. Yeah. All right. So
just a moment.
Sorry?
Just a moment. The slide you're from the previous slide. On your answer, why did you omit the 2 zeros for the first one?
This is what I'm saying. When you have the leading zeros, it's pointless to have the leading. They don't affect your answer in any way. Right?
All right. Yes.
They don't. You can put them there, by the way, actually. You can put them there if you want to. There's no harm in putting them there. But what I'm trying to say is that they don't affect your answer in any way. And in fact, your average application that you have out there, right? Observe, right? If you look at, if I change the representation of the registers if I represent them using binary. Now, registers, these are the 2-bit registers in MIPS, right? If I look at the value here, and I count the number of zeros here, what you'll notice is that, I hope this is the one. If I count the number of, this won't work, I guess, but I don't know. Right? So these characters here they're not 32, right? How many are they? These are 31 characters. You know why we've left out, why QT-SPIM leaves out a 0? Because it's a leading 0. A leading 0 doesn't affect the answer in any way. Right? So it's like me asking you, right? Or ask yourself this question. Are you going to get a different answer if you convert 111 to base 2 and if you convert 0111 to base 2? The answer is no, right? And we can prove this, right? So we get here and we're going to convert 111, 111, right? Let's convert this to decimal, actually. It'll be a lot easier. We'll convert this to decimal and then we'll convert 0, 1, 1, 1. When the leading zeros do not affect your answer in any way. Do you understand this? So this is because, why? Anyway, because, this is 2 to power 0. I hope dragging this will work. No, it doesn't. 2 to power 1, 2 to power 2. Right? What's the answer here? 1, 2, 4. Come here. This is 2 to power 0. 2 to power 1. 2 to power 2. 2 to power 3. How do we get the answer? 1 times 1 is 1. 1 times 2 is 2. 1 times 4 is 4. 0 times 8 is 0. Right? Answer here is the same, 7. Here it's going to be the same, 7 as well. You understand? But imagine a situation, yeah, but if you have the numbers that are supposed to be represented using 2-bit representation, if they appear in the middle, they're going to mess up your answer. Why are they messing up the answer? Because it turns out, right, when you're dealing with binary numbers, the more bits you have representing a number, the higher the magnitude, right? So if I have 1111011, and then maybe this was grouped using 4-bit representation, so 0, like this, right? If I have this number, and then, you see, if you look at this number, because of these ones that are here, this is a 1's place, 2's place, 4's place, 8's place, 16's place, and 2's place. The number is significantly larger when you have more bits representing that number. But if you have zeros at the beginning, it doesn't affect your answer in any way, right? So if I were you, though, I mean, doing this right now, I do highly encourage you to the answer, right? If you have if you have leading zeros, just put them there. You won't lose marks. If the answer is 0011, just put 0011 instead of saying 11, right? Oh, so not 11, instead of saying 11, right? It doesn't matter, it's the same thing. But your calculator, most of these tools won't allow you to actually have trailing zeros. Like if you look at what I'm doing here, I could switch to binary. I have 0, right? I'm typing 0 here and then 11. I can't. I'm not typing 0 because it's pointless to type the leading 0. Yes?
Yes, sir. Thank you.
Okay, great, good stuff. Okay, so I'm looking at the time here. I guess we'll go through the rules. I was going to say, oh, there's still more here, I guess. I thought we were going to transition to addition. That's fine. So converting large numbers is a lot easier, obviously. We can just latch on to this to this technique we've been taking advantage of. You just group them into nibbles, and then that's it. Convert the grouped numbers into equivalent. Oh, this is binary to decimal, right? Pretty trivial, right? Did we not do binary to decimal? I thought we did. Ooh, aha, good stuff. Now, here's the thing. This is another method, right? So if you remember, when we're converting binary to decimal, what we were doing was we were repeatedly multiplying. I don't know if you remember what we're saying. What we did last time, right? We were saying that if we had a number like this, yeah, and this is a large number, right? Observe, to convert this number into decimal, right? When you're converting a large number into decimal, our current approach has been that okay, is that okay, so we repeatedly multiply, right? Wait a minute, why is this thing? Okay, so we repeatedly multiply this, right? So we have 1, 0, 1, 3 ones, which is 1, 2, 3, 2 zeros. And then we have 1, 0, 1, 0. What we're saying, right? What we're saying is that sorry about the noise. I don't know if I said this. They decided to have a pool party somewhere close to where we live, right? Celebrating happy birthday or something. I don't know. Whatever that means. But anyway, so for us to convert this to decimal, what we're saying is we have to repeatedly, we repeatedly multiply this, right? Using the powers of 2 here, is it? 2 to power. We have the powers of 2. It's 0. Now I don't know how you'd write this, but it's 0, 1, 2. I guess we can drag this like Mr. Mwalimu has taught us in spreadsheet application. Ooh, we're going back in the opposite direction. I guess we can use formulas like he told us. So we will say, have you looked at formulas in EDU 1010? 1020, sorry.
Not yet.
Oh, I'm sure you will anyway. Okay, so observe, right? So what we're saying here is, and I'll just highlight these in yellow so that they don't distract us. So what we're saying is this is going to be 2 to power 0, all the way up to here, right? This is a method we've come up with, right? When we're converting binary to decimal. And then what do? We multiply these with the evaluated powers of 2. So it's going to be 1 times 2048, and then we can drag this formula here, right? And then finally we just add, and then we use the sum. They'll teach you these formulas, which is quite nice, I guess. So the answer is, wow, this is, none of us will be alive in the year 3018, right? This is 3018. At least I know I won't be alive, and I don't know about you. Maybe they'll discover something like life extension or something. So here's the thing. This is a method we are using to convert binary to decimal. But what we are saying here is that there's an easier method for you to, but at least for me, it's much easier. When you are converting large binary numbers to decimal, instead of doing this, I've tried to close the windows and they're still screaming and shouting, right? If instead of doing this, what you can do is you get your number, this number here, and then you break it down into nibbles. 1, 2, 3, 4. 1, 2, 3, 4. And then the next step is you convert each one of these nibbles into the equivalent hexadecimal numbers. And then you convert the hexadecimal numbers into decimal. Now here's the thing, right? The idea behind this is that it's a lot easier for you to convert from hex to decimal than from binary to decimal for large numbers. Think about this for a second, right? If not for a second, then maybe sleep over it tonight or something. Instead of watching those mindless movies, think about what I just spoke about here. Right, so what we're saying is there's 2 options, right? The first option is you can do what we've been doing where you repeatedly multiply, but the option that we're advocating for right now is we're saying we can group the binary digits in groups of 4s or something, right? So we group them into groups of 4s, and then we convert the groups of 4s into the equivalent decimal, and then we have, and this is repetition, I guess, it's equivalent hexadecimal numbers, and then this is supposed to be decimal anyway. So you have your decimal number, and then you convert it to its equivalent hexadecimal number, right? So 2-step process. You first of all convert the binary number into hex because it's a lot easier. You just break it up into groups of 4s or nibbles, right? You have your hex number, and then you get your hex number and you convert that hex number into decimal. How do you do this? Repeated multiplication by converting the symbols into their decimal equivalent and then multiplying them by their powers of 16. And in fact, at this stage, really, you could have multiplied them with powers of 16. Do you understand this? This is much easier.
Yes, sir.
Flip over this. Do a simple test, right? Try and see how long it's going to take you to convert a large binary number into decimal using this conventional method we introduced at the beginning. And then try and see how long it's going to take you for you to use this method we are talking about right now, right? I don't know. At some stage in life, you choose, right? Life is all about decisions. If you decide to use this method 2 where you convert direct from binary to decimal, that's fine. What I think is more appealing to me might not be appealing to you, right? But the only way you find out is if you experiment with these things, right? But don't experiment with stealing or any bad vice. All right, so this is what we're talking about here, right? Where you repeatedly multiply and then you get this. Now, the reason why you want to avoid this, right? The reason why you want to avoid this is because it is error prone. It's very easy for you to make a mistake when you're dealing with a lot of bits. Very easy. Our eyes sometimes will make us see things that are not there. I hope you've realized this by now. All right. And then obviously this is it. But take your pick, whatever works for you. Right. Again, here just trying to point out that a common pitfall, and I think I mentioned this, is to try and misrepresent the answers that you're getting, right? So if you break up a binary number like this into nibbles and then you convert it like this, you have 6, 7. Some people make the mistake of thinking that the 6, 7 is base 10. In actual fact, it is not base 10. You need to convert this into, this is base 16, you convert it into base 10, right? Assuming you're converting from, let's say, binary to base 10, for instance. It's very easy when your answer, the number you're dealing with, has has symbols that are shared with base 10. Is this making sense?
Yes, sir.
Yeah, I did mention this. I think, I don't know, it's probably like half a dozen times I'm mentioning this now. Just to put it out there again, that our focus in 1110 is on integer numbers and not really floating-point numbers or double numbers. These are coming your way in 2021, I believe, computational maths. I do encourage you to pay particular attention there, right? That course will open your mind up. You understand, you will understand computing a lot easier if you follow through with that course. Very interesting course. But anyways, so I'm looking at the time here. I was going to suggest that we start binary addition, but I think we'll stop here. I think this is quite a mouthful. We will start binary addition and hopefully subtraction tomorrow. We are meeting at 17 hours promptly, right? Unless if there are questions, I guess I'll just ask that we part ways and reconvene tomorrow or something.
When are you going to respond to emails?
I don't check emails over the weekend. I will respond to them probably by Monday. If I haven't responded to any of your emails, if they were sent either Friday or yesterday, for instance, it's likely I've not read your email yet, right? I normally take a break myself. So I'll probably respond by tomorrow or something, Monday, actually.
All right.
But if you sent me an email, maybe before last week and I didn't respond, please reach out to me. Then maybe I missed it or I accidentally archived it before actioning it. Great question. I'll see you tomorrow then.
Sir.
Yes. Yep.
So, you remember when you promised that you're actually going to give me a tutorial on how to do backups?
A tutorial on how to do backups? I don't think I did that. We're recording these sessions. Which session did I say I was going to do a tutorial on how to do backups?
The lab, not the tutorial.
Oh, right. Perfect. Great.
You said
can you send me a reply to that email? Yeah, a lab session. Reply to that email. I need to send that because I need space in my Dropbox. I have an interest in that. Can I ask that you resend that email, reply to it and say, following up on this item, please respond, and then I'll respond to that. Thanks for the reminder. Too much to do, I suppose, in life, right? Thank you very much. Stay safe. Bye-bye.
Okay, you've got 10 even reminding overlaps.
Leandro, da kumenya.
I think you don't have enough space.
Leandro,